So, hi everyone, welcome to this session of Biodynamics Days. It's our great pleasure to have today two talks. The first is from Isabelle Gallagher from Ecole Normale Supérieure, and the second is from Pierre Gabriel from University of Versailles till now. So the two talks today are related. I think it's an interesting question. So the first, so Isabelle is a very good and well-known specialist of Boltzmann equation, and so the limit how to go from the dynamics of each individual particle and this with the statistics how goes the limit and how you rigorously how you obtain under some hypothesis the Boltzmann equation. And the second one is somehow related because you obtain a PDE in the first case and in the second case also, but here I think Pierre is going to talk about some model, integrate and fire model, and he takes also a limit under some assumptions. And so I think it's interesting to have these two very good speakers on these two very interesting topics. So Isabelle, I let you speak.
Thank you very much. I hope you can hear me okay. Yeah, perfect. So thanks very much for the invitation. I'm really sorry I can't be on site today, so I apologize for that, but thanks for inviting me anyway. And so, yes, I'm going to talk about a subject I've been working on for a number of years now. It's related to relating the microscopic to macroscopic description of a gas or a fluid. So, so please feel free to stop me at any time, of course, right? I mean, I'll go as far as I can, and I'll be very happy to answer any question at any time. So please interrupt me if you like. So let me just start by some general facts about a gas or a fluid. So I'm talking about a glass of water here, but we'll see later on that actually what I'll be talking about relates more to gases, dilute fluids. So essentially, when you have a glass of water, it's made of a lot of particles of a very small diameter, and their velocity is very fast, so they're colliding constantly one with the other, right? And so if you want to describe the movement of each of the particles, one thing you can do is just write down Newton's laws for each individual particle. So this is what I've done here. So you can see on this slide, each particle is going to be assumed to be an identical hard sphere. Their mass is 1 and their diameter will be called epsilon. Okay, so this is this epsilon here. This is the diameter of my fluid. If you can see anything here. Yeah, this is epsilon. I'm not sure I can see what I'm writing here for some reason. Anyway, so the epsilon will be the diameter of the particles, and they're all going in straight lines. Okay, and so their velocity is v, and I'll label the particles with a letter I. Okay, so I is going from 1 to n, where n is the number of particles in my gas. So n will be very, very big. And so Newton's laws are just telling you that the time derivative of the position is the velocities. I'm sorry, I can't write here for some reason. Let's try again. If not, doesn't matter. I don't know why my pen is not working. So anyway, so the velocity is just the time derivative of the position, and I'm going to assume here for simplicity that the acceleration is 0. So that's the time derivative of the velocity is 0. Okay, so you could put a force if you wanted to, but just make things much more complicated, and nothing much is known actually in that case. So I just assume here for simplicity that the acceleration is 0. And so if particles weren't interacting, you just have these equations for each of the particles, right? So now that it's working. So the time derivative of the position is the velocity, and the time derivative of the velocity is 0. So here, the position, you should understand that as the location of the center of mass of my particle, which is here just the center of my hard sphere. Okay, so xi will be supposed to be in the whole talk in the d-dimensional torus. So we can talk later on maybe about what happens in more general situations, nothing much. And the velocity for each particle will be in the whole space. Okay, right. And so now what does happen is that my particles will collide, of course, quite often. And on collision, what we decide in this model is that the collisions are elastic. So I've given here the formulas which relates the incoming velocities, b primes, to the so that's the incoming to the outgoing velocities. But it's an evolution, right? So you could put primes anywhere you want in this equation here. So those are the collision laws giving you, relating the outgoing velocities, Vi and Vj, of my two particles, I and j, to the incoming velocities, V prime I and V prime j. All right. So omega here is a vector, a unit vector, which relates the centers of the particles which are colliding. So it's a unit vector. So if epsilon is very small, omega here will be very large, right? And it's the unit vector relating the centers of particles I and j. So it's in the sphere of dimension -1. Right, so you don't have to remember those relations at all. It's just the relations of Huygens or Descartes' laws for elastic collisions. Maybe all you can remember, if you want, is what's written at the bottom of the slide here, which is telling you that the momentum is conserved at collision, and the second equation here is telling you that the energy is conserved. Okay, the mass of my particles is 1. Is that okay? So these are Newton's laws. You can write down all these equations. It's a gigantic set of equations, right? Because each particle is in d dimensions. So you have essentially 2D equations here, okay? Times the number of particles, which is n, so 2nd equations. So it's a huge system of equations. And if you solve that system of equations, you'll know exactly where each particle is at each instant of time and what its velocity is. But at our macroscopic scale, it's obviously not so interesting to know where each particle is. Essentially, if you're in a room where nothing is happening, the air seems still. Nevertheless, each particle is moving all the time, like constantly. So from our macroscopic point of view, actually, it's not really the movement of each particle we feel, right? It's some kind of average behavior. So the question we want to address here is, if you start with this set of equations for each particle, it's probably not the right object to study. If you really want to know, for instance, what the temperature is of the fluid which is passing in front of you at some moment, it's probably not the right object to study. So what we want to do is to extract in some way some effective PDE, right? Which would tell you what we are feeling at our macroscopic point of view. So we have a huge system of ODEs. We want to replace that by 1 or 2 equations, which are PDEs. And now, one thing I haven't mentioned yet, which is written on this slide, is that the set of equations we saw before is reversible, time reversible. That means that if in the set of equations you change t into minus t, then it suffices to change all velocities into minus the velocities, and you get exactly the same set of equations. Okay, and another way of saying this is that if you take a movie of your system of particles, you play it in one direction or the other, nothing will change. Nothing will shock you. It's reversible. Okay. On the other hand, at our macroscopic scale, it seems that things are irreversible, right? If you've seen the Navier-Stokes equation before, or the Boltzmann equation, which we'll see in a minute, those equations are time irreversible. So we need to understand, in the process of extracting this effective equation, we need also to understand how reversibility has turned into irreversibility. All right, where did that happen? So before going into the more precise things, let me just show you this little movie you can find on the internet, which is known as the Ehrenfest paradox. So what we're going to see here is it's numerics, right? It's not a real experiment. It's a numerical experiment where you have lots of particles in a container, and then you have an empty container on the other side, and they're related with a little tube, okay? There's a corridor which link both containers. And at first, we put all the particles on one side, and then we let the system run. And since it's numerics and not real life, to make things as simple as possible, people have decided that particles can just step one over the others. They're not colliding. All that can happen is that particles are going to hit the side of the boundary of my container, right? But they don't collide. So it's a very easy model in some sense. And so let's see what happens. So at first, I have 200 particles on the left-hand side. And then you see once in a while, the particles go from the left container to the right one. And actually, once in a while, they also go from the right container to the left one, right? So they're in constant motion. And what you're counting here is how many particles are on each side. So you can't see probably what's written on the slide, but it doesn't matter. You can just see with your eyes that, roughly speaking, pretty fast, you'll have just about as many particles on one side as the other, right? It's of course not always the same particles, right? Because they're moving constantly from one side to the other, but roughly from far, at our scale, there are roughly 100 particles on each side. Rarely exactly 100, but often 110, 90, okay, something around 100 on each side. Now, what you can do here is look at one particle on its own, forget all the others. And since they're not colliding one with the others, they're totally oblivious to the others, right? Each particle is living its life and doesn't care about the others since they're overlapping. They're not colliding at all. So actually the movement of each particle is reversible, right? But now if you imagine, I'm not going to do it here because it doesn't work on my slides, but if you imagine the movie I just showed you, you're going to play it the other way around, okay? Reverse motion. What's going to happen is that you're going to have about as many particles on each side. And then suddenly the right container will totally empty and all the particles will be on the left. Okay, so each particle has a reversible movement, but it doesn't seem at all reasonable that all of a sudden all the particles are on the same side. Okay, so the overall movement we're looking at here is irreversible. If I play the movie in the wrong way, you'll tell me I played it the wrong way. Right? Because it's impossible that all the particles find themselves on the same side. So this is a paradox because I'm looking at something which is totally reversible as far as each particle is concerned. The particles ignore each other, but if you look at the whole system, it's irreversible. Right? And this is obviously linked to the number of particles. If I only had 1 or 2 or 10 particles in my movie, then I could have all 10 on the same side. 5, 4, 3, any number could be possible and just about as probable. But the thing is, if you now started talking about probabilities, what happens is that the number of microscopic configurations I can see here, meaning where each particle is at each instant, each particle has 2 possibilities. So if I have n particles, there are 2 to the n different configurations, right? Microscopic configurations. 2 to the n, since each particle has 2 possibilities. But from our macroscopic point of view, we don't care if it's particle 1, 2, or 3 that's on one side or the other, right? They're all indistinguishable. So from our macroscopic point of view, all that we see is that there are n particles on the left, or n-1, or n-2, or 0. Okay, we don't see which particle is where, which means that the number of macroscopic configurations is n+1, right? We have 0, 1, 2, 3, up to n particles on the left-hand side, for instance. So the number of microscopic configurations is exponential compared to the number of macroscopic configurations, right? There's a logarithm between the two, and this logarithm is actually what's known as the entropy. We'll see that later on. And this really measures the disorder in my system. If n is small, then n and 2 to the n are almost the same. If n is large, n and 2 to the n are very, very, very different. And so what's going to happen actually in this model is that if you wait long enough, if you wait like for 2 to the n minutes or seconds, it can happen that all the particles will be on the same side, right? At this scale, at the 2 to the n scale, at the microscopic scale, everything is reversible. But at the macroscopic scale, that's not the case. Okay, so now that we've maybe understood that, I hope, what we have to understand now is that the appearance of irreversibility is related to the scale of description. It's related to the fact that there are a lot of particles. Okay, if there are only 2 particles, then there won't be any fluids at the end. We just have Newton's laws. If I want to get a fluid equation, if I want to get something irreversible, I need the number of particles to grow to infinity, essentially. Right? So this was actually understood by Hilbert a long time ago. So he asked, you remember he had that list of 23 questions in 1900. And question number 6 he asked was, is there a way to have some kind of mathematical proof that you can go from the atomistic view, okay, so Newton's laws, to the laws of motion of continua, meaning fluid mechanics equations. And to do that, he mentioned the limiting process. There has to be a limit in some sense, in the number of particles, for instance. And what I didn't write here is that he also suggested using Mr. Boltzmann's book he wrote to try to go from particles to fluids. So today, that's what I'm going to do. I'm going to try to show you how you can hope to go from particles to fluids, and especially using the Boltzmann equation and going from particles to Boltzmann, actually. Okay, and then I'll talk a little bit about how you go from Boltzmann to fluids, but that would be the main goal of this talk. So if things are fine for the moment, let me try to show you what the Boltzmann equation looks like. So I'm sorry if there are a lot of people here who are specialists in this equation, but I just want to show it to people who've never seen it before and trying to show what each term of the equation stands for. Okay. So what Boltzmann was suggesting is that what he wants to do is, instead of studying where each particle is at each time and what its velocity is, we're going to try to characterize what the gas looks like by using what we call the distribution function, meaning what's the proportion of particles which at time t are in a tiny volume around x, right, and a tiny volume of velocities around v. Okay, so that's a density. This function f here is going to be a density, a probability distribution. Okay, this f here. It depends on time. It depends on the position I'm looking at and the velocity. But this is really reduced, right? I have a huge phase space anymore. I have one position in the torus, one velocity v in RZ, and I want to know how many particles, what's the proportion of particles which are sitting at that position, or which is around this position, and at that velocity. Okay, so again, this is not macroscopic. I can't measure this. But what you can do using this quantity is average it against all possible velocities. And that, by definition, will be the density of your fluid. That will be a function of space and time. Okay, if you take this function f and you average it against v dv, this will give you an average velocity. If you average it against v squared dv, this will give you some kind of temperature or energy. Okay, and what Boltzmann expects is that this average density, velocity, energy will be related by fluid mechanics equations. Okay, so if you write down an equation on f, so you have to figure that out. But if you manage to do that, then by integration, you should be able to find fluid mechanics equations. That's the plan. So the first thing you have to do is write down an equation on f. So here it is. And so if you've never seen it before, let me just go through each term of the equation slowly and try to guess why this is probably the correct equation. Okay, why Boltzmann was right in writing it down. Then you have to write down a theorem, of course. But for the moment, let me just give you this equation. This, by definition, is the Boltzmann equation. And let me later on state a theorem, but first of all, just explain why this is reasonable. So on the left-hand side, I guess a lot of you are familiar with a transport equation. Okay, so if you had 0 on the right-hand side, you would just be saying that to find my particle at time t, which is an x at velocity v, I just take the initial data and pull it back by x minus vt. Okay, that would mean if I had 0 on the right-hand side, that would mean that all my particles are going in straight lines. I'm just not so interested. But what we saw in the first slide is that actually particles undergo binary collisions. Okay, so pretty often they meet, they collide, and then their velocities jump by the scattering laws I gave you before. That explains why on the right-hand side you have this binary term, right? It's quadratic because I have binary collisions. This is a quadratic term. And f, remember, is a probability distribution, so it's a non-negative function. And so if I have something positive on the right-hand side, that means I'm increasing the number of particles at time t with position x velocity v. If I have a negative term on the right-hand side, that means I'm losing in proportion of such particles. And so let's see, for instance, here I see I have a minus sign, right? So this term here is saying that if I have a particle exactly of velocity v and position x, just like this function f here, what can happen is that it collides with a particle of velocity w for any w. W is random in the whole space, right? If that happens, then I've lost the particle of velocity v because after collision, I've created a new velocity, v prime. Okay, that's why I have this minus sign here. On the other hand, what can happen is that I have for any velocity w, I can have a particle of velocity w prime given by this formula, hitting a particle of velocity v prime given by this formula as well. And that creates a particle of velocity v. When I say create a particle, I don't really create a particle, but I increase the proportion of particles which have velocity v. Okay. So that explains why on the right-hand side here, I have this quadratic term. I'm increasing the proportion of particles with velocity v because of the collision with the particle velocity of two particles, velocity w prime and v prime, with those relations. All right. Now, the last thing I have to define here, omega is scattering cross-section in some sense. It's exactly the omega I gave you before in the first slide. And that's why I have this relation here. Omega can be anything on the sphere. Okay. And now this last term I haven't discussed, which is known as the cross-section. Okay, so this you can just understand in the following way. If I have two particles whose relative velocity, so v minus w, is perpendicular to their to the vector linking their centers. Okay, that means actually they're not really colliding; they're just gliding one against the other, and so there's no change in velocities, and this is zero. This makes sense. Okay, and the worst that can happen to you is for two particles that have relative velocities that are parallel to omega. That's a head-on collision. The worst that can happen, the strongest that can happen. Okay, so I'm not proving anything here. I'm just telling you this is reasonable to have such a term in this integral. Okay, it comes actually from a Green formula. You can of course prove everything, but we won't do that right now. But anyway, this is a sort of a crash course on the Boltzmann equation. So before stating a theorem proving why the particle system does converge to this equation, okay, I think a lot of you here are PDE people. So if we give you a PDE, you want to solve it. This is the first thing you want to do. And someone else can maybe explain why this is the correct equation, but you can also be interested in just solving it. So give me initial data. Can I construct a solution to this equation? Is it global? Does it blow up in finite time? And so on and so forth. So to do that, you're used to trying to find conserved quantities. Okay, a conserved quantity or a decaying quantity with time will be something that won't blow up in finite time, will be a good candidate to be a functional space in which to try to solve the equation. And so to find a conserved quantity, one thing you can do is take your equation, multiply it by some function, for instance, we call it phi, and then integrate, right? So take the equation, multiply by phi, integrate, and see what happens. If the right-hand side is 0, that means that quantity will be preserved by this. Okay, so what I'm looking for actually is functions phi, such that if I take q of ff times phi, I integrate in space and time, I'd like that to be 0. If that's 0 for any f, then the quantity f times phi will be conserved. Okay, so can I find a function phi such that for any f, q of f times phi, integrate over x and v is 0. So first thing we can do is integrate it against v, and then you notice that everything is totally symmetric with respect to v and w once you've integrated against v. So I can very well say it's 1/2 of the integral against v plus phi of v plus phi of w, because it's symmetric. But what we can also do is change vw into v prime w prime. That will change actually omega into minus omega, and it won't change anything in the formula. So in the end, up to putting a 1/4 here, q of f times phi integrated over v is 1/4 of this guy here. Just using symmetries of the collision integral. So for this to vanish for any f, I need this guy to be 0. Okay, so I need to find a function phi such that this equation holds. So there's an obvious case when this equation holds is that when phi is a constant, right? Because 1 plus 1 minus 1 minus 1 is 0. There's another case when that is 0, it's when phi of v is identity, because v plus w is equal to v prime plus w prime. Okay, it's conservation of momentum. And then there's another case when that's 0 is when phi of v is v squared because of conservation of energy. Okay, and actually you can prove that's the only possible route. So that's a theorem in some sense, that the only way for this to be 0 for any f is for phi to be either a constant, a linear in v, or quadratic in v. Okay, so this is telling you that the Boltzmann equation remembers that at the microscopic level, you had conservation of mass, which was 1 at the macroscopic level, momentum and energy. Right? Now, one other property, which is a bit less obvious, is if you do the exercise I gave you before with phi and replace phi by log of f, okay, and then use the properties of logarithm, like log f of v plus log f of w is log f of v times f of w. Use that, use the properties of convexity of the logarithm, and you find this quantity is non-positive. Remember, the logarithm was a measure of entropy, and this is exactly telling you that the entropy is increasing, well, decreasing in this sense, that the physical entropy is minus this one. So the entropy is decreasing, mathematical entropy is decreasing with time. This is useful. This is telling you that that's another quantity that won't blow up in finite time. This is also telling you that the dynamics at the Boltzmann level is irreversible because I have something which is decaying in time. Okay, so I can't change for free t into minus t, if not that would be increasing. Whereas Boltzmann is telling you it's decreasing. So to go from particles to Boltzmann, I need to understand that. I need to understand why suddenly I have a irreversible equation starting from a reversible system of equations. So that was a big issue at the time of Boltzmann. It's called the H theorem. H like entropy. H is a capital eta. Eta is the first letter of entropy in Greek. And so that was especially Loschmidt was very angry at Boltzmann for that. So there was a huge controversy saying, how can you get an irreversible equation from a reversible system of equations? So now this is very well understood, but at the time it was quite an issue. Anyway, so okay, we can try to remember this. The last thing we can wonder, which is very important to solve the equation, is what are stationary solutions? Okay, equilibria. Obviously, 0 is a stationary solution. And another stationary solution would correspond to asking for this entropy to be constant. It has to be constant. If you're stationary, that will be constant. So that means Q of ff times log f has to be 0. If you want f to be stationary, that means that log f has to be a constant, or v squared, which means f has to be exponential. And since it's also it's also an L1, it has to be a Gaussian. Okay, so we'll call those Maxwellians. Those are stationary solution of the equations. They actually here cancel each term of the equation. And this is a useful function, right? This function is solves the equation globally, stationary. So now to solve Boltzmann, what you can do is two things. Either you say, well, let me use the entropy and get a global solution because I have a global control of the entropy. Or let me use this M, the stationary solution, and try to solve the equation around this M. Okay, so both things have been done. The first result I want to state here is telling you that if you don't use anything, you can use just a kind of fixed point method to get a unique solution on a small time interval. Okay, so essentially, for instance, if the initial data is smaller than the Gaussian, then up to losing a little bit in your Gaussian, you start with 1/2, let's say you get to a quarter, then you get a solution for small t. Okay, which depends on C0 and beta 0, and the fact that you went from 2 to 4. Okay, now if you want to get a global solution, you need to ask, that's a result by Ukai in 74, you need to ask for your initial data to be close to M. Okay, in that case, you can do a fixed point around M and you get a global solution. If you don't want smallness, then you have to use the entropy, and so it's much harder, it's more recent results. The solutions are global, they're not known to be unique, and actually they're not classical solutions, they're not even distributional solutions, they're renormalized solutions, but I won't say much more about that unless you ask me. That's a global picture for Boltzmann, okay? So either you're close to an equilibrium, you have a global unique solution, or you're anywhere smooth enough and you have a local unique solution, or your entropy is finite and you have a global, possibly non-unique solution. Okay, so now my original question was going from particles to Boltzmann. So can I do that? Sorry. My first question was going from particles to fluids. So as I said, we won't do that today, but I just wanted to give you the recipe to do that. The recipe is to say, let me stick in the equation, inside the equation, the mean free path, alpha, which is very, very small. It's telling you essentially the time you have to wait for before 2 collisions. Okay, so this is a parameter you could add to the equation using some dimension analysis. Let me put it here, it's 1 over alpha. Alpha is going to 0. And now the idea is to say, let alpha go to 0, do what I said before, integrate against v dv, and v squared dv. And then there are theorems, I'll show you in a second, saying that the solutions to those equations, to this equation, when you do what I said, you integrate, you let alpha go to 0, those solutions do converge in some sense to fluid mechanics equation. Okay, our plan is to go from particles to fluids, and I'm telling you there is a way to go from Boltzmann to fluids. Let me make this more precise now. So Hilbert wants to go from particles to fluids, and so the idea is to say, let me let the number of particles go to infinity. When I do that, I need to let their diameter go to 0. I'm in a fixed box. Okay, and I also need to let alpha go to 0. Alpha is the mean free path. Okay, now there's a relation between n and epsilon, which is linked to the title of this talk, which was dilute gases. The relation is the following. I'm going to ask for, well, it also relates actually alpha. Alpha is the mean free path, so it's essentially the time I have to wait between 2 collisions. And this is related to the volume occupied by each of my particles. Okay, so in other words, what I want to ask for is that in time, let's say 1, another way of understanding the mean free path is to say in time 1, an average particle will have hit 1 over alpha others. Okay, it's just a rescaling of what I was saying before. So assume that, or for instance, I have one particle here of diameter epsilon. In time 1, if its velocity is essentially 1, the volume is going to occupy, if it goes in a straight line, is epsilon d minus 1. Okay, it's the volume of this cylinder based on the sphere of diameter epsilon. Now, if I want this particle to have 1 over alpha collisions, since I have n particles around me, or n minus 1 particles around me, it's telling me that n minus 1, or n, which is roughly the same, times this volume has to be equal to 1 over alpha. Okay, that is a way of defining the mean free path. Okay, so the scaling I'm going to use here, which is known sometimes as the dilute gas scaling or the Boltzmann-Grad scaling, is exactly that. The number of particles is related to their size by this formula here. Okay, if you don't like alpha, take alpha equal to 1. But if you want to get fluids, you'll have to let this alpha here go to 0. That means that when alpha is going to 0, that means there are more and more collisions. Okay, so my gas is dilute, of course, because the volume occupied by the gas is very small if alpha is fixed. But if alpha is going slowly to infinity, then you see that this is going to infinity. This is the parameter going to infinity, which will give me fluids in the end. So let me just give you some results. So actually, essentially nothing is known if you want to go from particles to hydrodynamics directly, okay, without using Boltzmann. To my knowledge, at least, the only results are known are usually on lattices. Okay, so you put particles on lattices, and you assume, for instance, that when they collide, when they change a point on the grid, then their velocities change in a random way. Okay, that's an example. So in that case, with noise added to the dynamics, then there are a lot of results relating my gas to fluid mechanics. Okay, I gave some examples here. But in our context, we like really to start from Newton's laws. We don't want to put any noise initially, and we still want to find hydrodynamics in the limit. That's the plan. So we want to use Boltzmann. And the idea is to say, okay, let me start by going from particles to Boltzmann by letting the number of particles go into infinity, epsilon go to 0, and fix alpha. Okay, then I should get the Boltzmann equation with 1 over alpha on the right-hand side, like I showed you before. Then plug in theorems telling you, well, Boltzmann, when alpha goes to 0, does converge to many subspaces. Okay, so the hope is to do that in 2 steps. One step doesn't care about fluids, just I want to find Boltzmann, and then I want to plug in results going from Boltzmann to fluids. That's the idea. So actually, there are a number of results relating Boltzmann to fluids, which is not the goal of this talk here, but I just gave you probably the most important results. So there are many theorems, I can tell you more later on, saying that under some scaling assumptions on time, if you want to get Navier-Stokes, you have to wait for a very, very long time. Time 1, if you want to get Euler, compressible Euler, there are theorems, a number of theorems relating Boltzmann to fluid mechanics. So for today, let's just assume this is fine, this is known. What I want to do is go from particles to Boltzmann, and then I'll just plug in those theorems. Okay. So let's see how that works. So I guess for the moment, things weren't too, I hope weren't too technical. The coming slide might be a little bit more technical, but I hope it won't be too long and too painful, but please tell me if there's any problem. But let me just show you how it goes. What's the object you should study if you want to find Boltzmann? At the moment, I had this huge system of particles called Newton's laws, huge system of equations. I want to get just one PDE. So what's the object of the particle system that will converge to F solution of Boltzmann? So the object is going to be the following. So first, let me give you the setting, the phase space. So the phase space is given by a collection of positions, okay, n positions, n velocities. Capital V is the collection of velocities, capital X is a collection of positions, and capital Z is the collection of everything. Okay. And this Z is living in the phase space given by this constraint here, which is recalling that particles don't overlap. Remember, epsilon is the diameter of my particles, so I need my functions to live in this phase space here. I'm not allowed to have xi minus xj smaller than epsilon. That's just forbidden. Okay, so this is very important. And now all I can do is set my initial data. So I have a huge system of particles. Let me just decide how they are at time 0. And then I want to let everything go with the flow of the Newton's laws, and I want to find Boltzmann. So what's my initial data? That's the only thing I can play with. And here it is. So sorry, this is going to be painful. Let me go slowly. The first thing I want to do here is assume all my particles are initially set in the same way. This is this product here. That means they're tensorized. Each particle from 1 to n is living with this probability distribution f0. So I don't know exactly where they are, right? But their probability distribution is f0. Okay, so if f0 is a Gaussian, then nothing will happen. If f0 is not a Gaussian, my question is, how will this evolve in time? Okay, so initially they're essentially independent, but living this under the same distribution, f0. They're identically distributed, and I want to know what's going to happen with time. Now, I also need to remember my particles don't overlap. So this is this guy here. Okay, I remember Zn is in the phase space. And what I want also to do is to assume the number of particles is not fixed. So that was not exactly what people did at the beginning, but it's actually pretty useful to do that to understand fluctuations. So let me do this today. So this is what's called the grand canonical formalism, meaning that the only thing I know is the average number of particles, which is given by this. When I write this expectation, that means against this probability distribution. If my number of particles is n, the average number of particles set alpha equal to 1 here. I have no more alpha, right? I don't care about alpha going to 0, so I'll just take alpha equal to 1. Okay, so my average number of particles, which I call mu epsilon, times epsilon d minus 1 should be equal to 1, right? That's the Boltzmann-Grad scaling. Now, if you do this Poisson distribution for the number of particles, right, you can check that the expectation of n is exactly this mu epsilon. That's just the Poisson distribution. Okay, so the number of particles is not fixed. All I know is its average. And then I just divide by this partition function, and I get something which is a probability distribution. Okay, so my initial data is all my particles are identically distributed. The average number of particles is 1 over epsilon d minus 1, and then I just normalize it. Is that okay? So that's, I guess, probably the worst part of this talk is just setting up the initial data. Once I've done that, my question is, where does this f0 go as time evolves? Okay, or also where does this w go as time evolves? So actually w is easy, because since my particles solve, I mean, I know exactly what they're doing, each particle, right? They're going straight lines and they collide. So the probability distribution of my n particles just satisfies a transport equation, because all particles go in straight lines unless they collide. Colliding means this guy is living on the boundary of my phase space. Okay, so what I have to do is just add to this transport equation boundary conditions. Okay, what happens if xi minus xj is equal to xi? And if that happens, what you do is change the velocities of those particles hitting the boundary by the scattering I gave you before. Change vi to v prime I. Okay, so my huge set of particles, n, for any n can be anything, okay, satisfying this kind of Poisson distribution. The huge set of Newton's laws just becomes this PDE in this phase space, which is gigantic. Okay, this is still not Boltzmann. To get Boltzmann, what I have to do now is to integrate this function against all particles except for 1. Okay, so that's the idea. You have this transport equation in the huge phase space. And now what you do is just look at the integral, or in some sense, the empirical measure. Okay, this is this we have to understand. Take a function h, which is continuous. And what you want to do to get the Boltzmann equation is look at the empirical distribution computed at h, meaning, in other words, computing this quantity here. Okay, if I compute this, by definition, it's a function of one variable. Okay, so I've totally reduced the phase space. I used to have a huge n-dimensional phase space. Now I look at this function f of one particle, okay, defined by this object here. And the claim is, so this is telling you, this is in some sense the probability distribution of one particle. Okay, and the claim is this function f converges to the Boltzmann. Okay, this is a correlation function with one particle only. Okay, so there's no correlations. It's a distribution function of one particle. To compute it, this is a totally given function. I know exactly where each particle is at each time. Okay, I give myself any function h, compute it at this configuration, zi, take the average. take the expectation with respect to my initial data, which I gave you before. By definition, this gives you a function f. And the claim is this function f epsilon converges to f solution of Boltzmann. So let me state the theorem. This is a theorem due essentially to Lanford in 74, although a lot of people worked to make his proof a little bit more solid in some sense, but most of the 99% of the work was done by Lanford. So what he's telling you is exactly that. Assume each particle is distributed according to F0, as I told you before, up to the exclusion. Okay. Assume F0 is continuous and bounded by a Gaussian. That was the same assumptions we gave for Boltzmann. And then this function I just defined before converges as the number of particles, the average number of particles goes to infinity, uniformly towards the solution of the Boltzmann equation with data at 0, of course. Okay, so that's exactly what he wanted, right? He does more than that, actually. He even tells you that if you look at any set of n particles and you compute the n particle correlation function, meaning you take a function of n variables and to look at the correlations or the function of any set of n particles, okay, any number ij, ik, look at any set of n particles, take the average, the expectation with respect to the initial data, and this defines the n particle correlation function by definition. What Lanford proves, and it's actually necessary to get the theorem, is that this n particle distribution function converges to n copies of the Boltzmann. That's known as the propagation of chaos. It tells you that if initially all particles are independent, then when the average number of particles goes to infinity, they become again independent. Okay, if you have a fixed number of particles, they can't be independent because they're hitting each other. They're not independent. When two particles have just met, they're not independent. They're just met. But when you let the number of particles go to infinity, actually, it's true that in the limits they are independent. Okay, and that's exactly what he proves. And this, okay, so I had planned of giving a sketch of proof, but I guess no, I won't do that because for lack of time. So what can I do? Maybe I'll, okay, just close your eyes for a second and I'll just remove the proof, which is a little bit long, but it's gone. It's gone. Okay, so you can open your eyes again. So to prove propagation of chaos, as I just said, what he says is that if two particles meet, then since they're supposed to be independent, that means they haven't met before. Because if they have met before, then they're not independent on collision, so that his theorem cannot be true. Right? So to prove this propagation of chaos results, that means you have to eliminate recollisions. You have to eliminate the fact that when two particles meet, they actually had met before. So it's actually a recollision and not a collision. You actually have to also forbid the fact that when two particles meet, maybe they hadn't met before, but they met particles that met before. Okay, so the whole collision trees have to be independent. And once you notice that, you understand that irreversibility arrives exactly here, because when I'm talking about a recollision, I'm talking about an arrow of time. I'm talking about the future. Okay, so there's a way actually of stating and proving a Lanford's theorem, which really shows exactly why the statement and the proof are irreversible and why the Boltzmann equation is irreversible. It's totally written in the statement of Lanford's theorem and its proof. Now, okay, so I guess I'm running out of time. So all I want to say here is that the main problem of Lanford's theorem is, as I said, the theorem is true on a short time interval. Okay, you might have seen that in the statement. The statement tells you, give yourself initial data. There is a time such that F1 converges towards F. And this time depends on the constants C0 and beta 0 I told you about. Now, the thing is, remember what we want to do is take Lanford's theorem and then plug in convergence alpha going to 0. Okay. Now, the thing is, if you replace Boltzmann by the same Boltzmann with 1 over alpha on the right-hand side, what happens is that the time of existence, if you replace 1 by 1 over alpha, becomes alpha t, just by scaling. Okay, so if you take Ukai's theorem with time t, you put 1 over alpha on the right-hand side, t becomes alpha t. But alpha t is going to 0 as alpha goes to 0. Okay, so there's no way you can plug in results going from Boltzmann to fluids because Lanford's theorem just breaks down when alpha goes to 0. It's true on time 0. Okay, so the main problem in Lanford's theorem and the proof, and no one can do any better for the moment, is to replace this alpha t by something going to infinity, or at least fixed, okay, bounded by from below when alpha goes to 0. So to this day, we can't go from particles to fluids because we're unable to do better than Lanford's theorem, which is a short time, and if you rescale, it's for a time going to 0. So maybe if you let me just, Benjamin, just for 1 more minute, I'll just, yeah.
Yes, please go ahead. Yeah.
I just want to conclude this by some sort of recent results, not so recent now, which improve this in linear cases. So maybe I'll just stop with these last slides, which tell you that in some linearized settings, you can do better than the Lanford's result. You can actually improve it to get fluids. Let me just finish with that. So the first thing we did, that was quite a few years ago with Thierry Boudinot and Laure Saint-Rémy. We did the following. As I said before, the only choice you have is the initial data, right? I mean, once you give yourself your initial data, then you just run the equations. You can't do anything more. The equations are working for you. So the only thing you can play with is the initial data. So one thing you can do is do something much simpler than just taking all particles identically distributed according to F0. You can say, I know that if F0 was a Gaussian, everything would be stationary, nothing would happen. That's not very interesting. But now let me just assume that everyone is at equilibrium, all my particles, except for 1, for instance, right? Or a finite number, but let's say the finite number is 1. That means we're looking at a tagged particle, right? All my particles are identical except for number 1, which I put a little label on number 1. And let's say, for instance, I take it and I move it, I put it somewhere else. Okay, or I change its velocity, I change its position. I do something which means that that particle is not at equilibrium anymore. Then I let the system go. And what's going to happen is that this particle is going to hit a particle at equilibrium, which of course will not be anymore at equilibrium. And then those 2 particles will start hitting others, and then chaos in some sense will appear. And my question is, what's the equation satisfied by this tagged particle as the number of particles around me is going to infinity? Okay, so you can just follow Lanford's proof. And what you find is that the Boltzmann equation becomes a linear Boltzmann equation. So maybe if you just give me 1 second, remember we had Boltzmann, which was bilinear, so you can linearize Boltzmann. If you do that, you'll get dTf plus v greater than xf is equal to 4 terms, right? Because I have q of ff is going to become like, f of v prime m prime of w prime, guess put a 1 here, minus m prime f prime 1. That means I'm integrating against v1 plus, whoops, oh, that's bad. Sorry about that. Okay, so this is gone. Okay, so anyway, you linearize, you get 4 terms, right? You linearize a bilinear term. Now, if you, on those four terms, you decide to kill 2 of them for some reason, I can't explain now, right? For lack of time, you get a linear equation again with a little bit less terms. And this linear equation converges to a Heat equation when alpha goes to 0. That's easy to prove. Okay. But what's interesting is that because everything's linear, because you have some kind of a priori estimates which are much better than Boltzmann, L log L becomes L infinity actually in this setting, then actually the theorem going from, the theorem which allows you to go from particles to fluids actually holds for a time going to infinity. So a time t alpha, let's say, which goes to infinity when alpha goes to 0, which is much better than alpha t1. So you can relate actually epsilon, n, and alpha to do all the limits at the same time. And it tells you that at the limits when n goes to infinity, epsilon to 0, alpha to 0, your tagged particle is going to satisfy a Brownian motion. And its density will satisfy a Heat equation, which is the easiest equation we can think of, which is a fluid mechanics equation. So in this setting, you're able to do the whole program going from particles to fluids for a very, very particular setting. And the last thing I want to talk about before stopping is something a little bit more fluid type. Heat is okay, but you want to get something like Navier-Stokes. And so you can look at what happens when you linearize the Navier-Stokes. The linearized version of Navier-Stokes is called the Stokes equation, okay, which is I got right here, but just you kill the nonlinear term. So it's possible to get the Stokes equation if you assume in some sense that each particle now is a perturbation of the equilibrium. Okay, not just one. It's just not just I take one particle, I move it around. I just say each particle looks like the equilibrium. If you do that, then you do get the exactly linearized Boltzmann equation, the 4 terms on the right-hand side. And this linearized Boltzmann equation is known to converge, it's not hard to prove, to the Stokes Fourier equations. Okay, so, and you're able to prove the limits from particles to Boltzmann, again, for a time going to infinity with alpha. Because you have some a priori estimates, which are much better than L log L. It's actually L2, which is a linearized version of L log L. And using this and working a little bit, you can prove both limits. And that theorem also tells you that you can go from particles to fluids, but again, in a totally linear setting. So, okay, so I'm past my time. So just to conclude what we're trying to do. So recent things we have done, I'll just stop here, is to try to do better than Lanford, is to try now to understand fluctuations around Boltzmann, large deviation theorem, so that works. And okay, so hopefully one day someone will be able to do much better than Lanford and get fluid dynamics. For the moment, all we can do is understand fluctuations around Boltzmann, large deviations, and okay, so we're trying to understand a little bit more what's going on in this proof to try to improve the results. Maybe one day someone will find a fluid equation, a proper fluid equation. Okay, sorry for being a little bit late, and thank you for your attention.